I'm Dave, and I'm making my gear.
Welcome back. How far are we into this thing? What part are we at here? Hold on. What part are we at? We are at part 5 of the ESP32 SK1 sampler. It's a whole foot's worth of videos, people. Oh boy, I need to get out more. What are we doing today? We have the keypad hooked back up. It took a lot of code to get this thing working, so we have a lot of code to go over today. So I think the best move is to cut the chit chat and jump right into the code. Okay, so if you've been following along, some of this stuff is going to be redundant, but I'm just going to go through everything to explain the code. All right, audio settings. Here we define some important constants. The mic input pin is GPIO32 and the audio output is GPIO25. That's the built-in DAC pin on the ESP32. The sample rate is set to 9,380 Hertz. This rate was chosen for a couple different reasons. It's to match the SK1, and also the lower sample rate saves memory and gives us like that gritty character to the sound. The recording duration is 1.4 seconds, and the total number of samples is calculated by multiplying the sample rate by that duration. The sample count determines how big our audio buffer needs to be, right? And this is setting up our audio buffer, okay? So next we have our button matrix set up. There are 4 rows and 8 columns, so that gives us 32 buttons in total. I use this matrix scanning technique because it's super efficient way to read lots of buttons with fewer GPIO pins. The rows are set up as input with pull-ups, and the columns are outputs. We scan by pulling one column low at a time and then check which rows are pulled low, meaning which button is being pressed. And then we have our playback variables. These variables keep track of the playback state. Is playing is a simple flag that says if something is currently playing or not. Playback index is a float which points to the current position in the audio buffer. Using a float instead of an integer allows smooth pitch shifting. More on that later. Playback rate controls the speed of playback, which directly affects the pitch. For example, if it's 2.0, the sample plays twice as fast. That's an octave higher, right? And then we have some note names that are used for debugging. Setup. In the setup, I initialize the serial monitor so I can see debug info. I set the mic input pin mode and set the audio output to 0 initially. I also set the pins for the button matrix, rows as input pull-ups, and columns as outputs, which are initially set high. Then I allocate memory for the audio buffer dynamically using malloc. After that, I call recordAudio. This records 1.4 seconds of audio from the mic and stores it in the buffer. Finally, display summary outputs some stats about the recording like min, max, and average values, which helps us debug and understand the signal that we actually recorded. Now for the main loop. This is where the magic begins. So what's happening here is we're pulling each column low. Then it reads each row, and if the row reads low, it means the button at that row and column intersection is being pressed. Then, when a button press is detected, it sets the playback rate depending on which button was pressed. So this is where the actual pitch shifting happens, right? It resets the playback index to 0 and sets is playing to true to start the playback of the sample. When the button is released, it stops the playback and sets the DAC output to 0 to prevent any leftover noise from happening. Then we set our columns high again. We jump to handleAudioPlayback and it loops over and over and over again. So let's go to recordAudio. So recordAudio, we loop through the number of samples that we have, right? Then we wait the correct amount of time based on that sample rate. So approximately every 106 microseconds. Then we read the analog input from the mic pin. That's a 12-bit ADC value ranging from 0 to 4095. The issue is that our DAC is only 8-bit. In this line, what we're doing is we're taking that 12-bit number and we're shifting it over 4, okay? 4 spaces. That converts that 12-bit number to an 8-bit number. So from 0 to 255. What that allows us to do is save a little bit of space and memory. It also matches our desired playback resolution, right? And then we take that data and we store it in the audio buffer, okay? So next we have our handleAudioPlayback. This is the part that's actually going to correct the pitch based on which button we're pressing, right? So we're taking our playback index as the current position in the buffer. And then what happens is we're doing fractional stepping, which means we're smoothly interpolating between samples when playing faster or slower to avoiding like a choppy sound, okay? So we do a little bit of linear interpolation here between 2 adjacent samples based on the fractional part of the index. Then we write the interpolated sample value to the DAC pin to output the audio. It's super complicated. I've kind of, doctored this based on kind of like other existing code. So I don't have a super deep understanding of it, but I know that it works. It's complicated. Okay, and then let's just jump down to the getPlaybackRateFromButton. Okay, I'm using C3 as our main middle pitch, and then we're doing some math to figure out how to do the offsets of semitones for each key. I go into a little bit more detail in the Medium article on how this math is actually done. Okay, but that's it. That's all of our code. Before we get to the demo, the gain circuit for the microphone input, I had to make a slight modification. The gain is like super high in this configuration because I've got the input resistor is 1K, the feedback resistor is 470K, so it's got a huge gain on it, right? It's like 471. In last week's video, when we were just recording and then looping playback, it sounded fine, right? It was crunchy and a little bit noisy or whatever, but once I added the keypad and the pitch shifting stuff, things got kind of weird and the sound quality dropped a lot. Basically, from my understanding of it, is that with the gain and the processing, weird stuff gets accentuated. So it was like super duper clippy. So what I did here was I reduced this 470 to 100K. So I reduced the gain a lot in order to get the playback to be like noticeably better. As I said before, this microphone is going to be replaced. It's just a prototype, but to have a prototype that is actually listenable, we had to reduce the gain. So just pull out your 470K, stick in 100K, and you should be pretty good. All right, let's test this out. We got the sampler hooked up to the little mini amplifier, and we'll sample something real quick, and then we will do some pitch playback. Let's go. It works! It works! It works! It works! It really, 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 really works! Well, there you go. We have something that resembles a musical instrument now, which is great, which is what we want. Next week, what are we going to do? Record button has to get done. Loop set button has to get done. I want to do like an LED that indicates that we're actually recording a sample. I also want to add an LED that indicates to us that something has been stored in memory after we sample it. So there you go. That's the plan. So if that's something that interests you, jamon, subscribe to the channel and hit that notification thing. And thanks for watching. I'll see you next time.